In this Math 12 lesson, we're going to look at using regression. And in this lesson, we're particularly going to focus on linear regressions. And then in the next lesson, we can build off this idea. Our goals are to be able to graph data and decide what kind of polynomial best fits the graph. So this lesson is going to let us learn about the line of best fit and the related vocabulary. Our course also expects that we can use technology to solve a problem involving a polynomial function. So in this lesson, we're going to be using a TI to find an equation to fit linear data and also to help us make predictions. You may remember that at the start of this unit, we looked at some scatter plots and tried to come up with some patterns. We're going to be building off those ideas now, and especially developing abilities so that everyone ends up with the same answers. To start with, one of the vocabulary terms that we should recognize is the idea of a scatter plot, showing a group of individual coordinate points. We can do this with technology or by hand, keeping in mind that when we create a scatter plot, each of the points is individual and we don't connect the dots. If we're going to do a scatter plot by hand, we'll have a table of values and either be given a grid or create our own. Keeping in mind we should have a scale drawn on the x and the y-axis that's consistent. If one box is 1 unit, it should stay consistent for the entire axis. Here's my first data point where x is 1 and y is 8. And we'll continue filling in the data points. And here's our finished scatter plot by hand. When we're talking about creating scatter plots, or later on talking about regression, we'll use the language of independent variable, which is what represents our x values and goes on the x-axis. It will either be the first column in the table, or if we have a horizontal table, it'll be the first row. We also talk about the dependent variable. It's what goes on the y-axis, either in the second column or the second row. To create a scatter plot on our TI, we're going to start out with the statistics button, right here underneath the delete key. When you press the statistics button, you'll get a menu that looks like this, and we choose the first option to edit. We put our X data into list 1, and our Y data into list 2. Before you look at your scatter plot on your TI, you should make sure that there are no equations in the y equals space, so you might have to push the y equals button to check. When you're ready to create the scatter plot, you'll push the second button, then y equals. That'll bring you to this screen. We want to edit plot 1, so we'll make sure that we've highlighted that 1 and push enter. We'll select on and choose that first option of the scatter plot to tell the calculator what we'd like to see. The last steps are to make sure that we can actually see our scatter plot on screen. So we're going to push the zoom button just in the center underneath your calculator screen and scroll down until you find the option numbered 9, Zoom Stat. Once you do that, push the graph button and we should see our scatter plot on screen. Some common problems that students have. If we make errors entering the data, either mistyping a number so that we get a wrong coordinate point, or skipping an entry so we don't have complete pairs of x and y coordinates. To avoid this mistake, it's a good idea to proofread your lists before you continue. Another common mistake is accidentally deleting a list. To avoid this, when we want to empty out a list, use the clear button and not delete. If you've accidentally deleted a list, ask me for some help fixing that. The other common problem that students will have is leaving another equation to be graphed in the y equals spot. That's pretty easy, just clear out that equation. So when we talk about scatter plots, this connects to one of the goals of the course, where we can look at some messy data in a table or a scatter plot and find a polynomial equation to model that data and make predictions with. In other words, we want to find a line or a curve of best fit. At the start of the course, we did this by hand, and unfortunately, we got slightly different sketches and so slightly different answers. When we were creating our sketches, we were either finding a line of best fit for a straight line or a curve of best fit for the data that looked either quadratic or cubic. From here on out, rather than trying to use our best guess, we're going to use technology to do regression analysis. This will allow us to find the line or curve of best fit using statistical analysis, and the benefit is that now we all get the same answer because we've all done the same process. In this lesson, we're going to focus on a linear regression. So we're going to start out entering data into our calculator the same as if we would do a scatter plot. To run the regression, you're going to push the Stat button and then arrow over once to get to the Calculate menu. We choose the fourth option, the linear regression, and push Enter to bring that to the main screen, and you'll need to push Enter again to actually run the regression. Here's what you'll see on screen. Your calculator reminds you of standard form and then tells you the values to fill in. So when we actually record our equation, we'll record those filled in values. In this case, y is equal to a, or about negative 0.64x, plus b, or about 8.67. Your calculator should include some other values on screen as well. We're especially interested in this r-squared value. The r-squared value is our correlation coefficient. It measures the fit of the line. The closer that your r-squared value, or correlation coefficient, is to 1, the better a model the equation is. If you don't see r-squared on screen, we'll talk about that in just a moment. Just before we talk about getting that r-squared value, this is a good time to remind all students that you should round to 2 places after the decimal unless the question tells you otherwise. So if you don't see your r-squared value, there's a one-time fix. To get r-squared, you need to turn your diagnostics on. You're going to push second and then the 0 button to get to your catalog. Push the x to the -1 button just underneath x squared. This is going to jump you to all the different commands that start with a D. You're going to scroll down until you find the diagnostic on command. Press Enter twice, and you'll turn your diagnostics on so that all your regressions will show the correlation coefficient. You'll have to run the regression one more time, but now you'll see your r-squareds. Once you have your equation of the line of best fit, you can see it on top of the scatter plot if you need to. You can simply type the equation into the y equals place, and then press Graph again. This will allow you to quickly calculate the value of y for particular values of x, or to go look at the tables of values if that might help you out. The advantage of finding a line of best fit with regression is that this is going to be much more accurate and far less prone to human error. It makes it easier in class for us to check our work and compare answers, and then we all get the same sorts of responses when we use these equations to make predictions. Speaking of making predictions, there are 2 terms that we should recognize as part of Math 12. To interpolate means to make a prediction that falls inside the data set. And when we interpolate, our predictions are much more likely to be accurate. To extrapolate means to make a prediction outside the data set. So let's look at an example where we put this all together. So we're going to take this data. Our first column is going to be the independent variable, the x, which will go into list 1, and the second column is going to be the dependent variable, the y, which will go into list 2. Take a few moments to put this data into your calculator and run the regression. Press pause while you do this. When you're ready, continue the video. We should find that this turns into y is equal to 0.20x subtracting 13.42. And we find out that our r-squared value is about 0.57. So is this a good model? Well, it's okay, but it's not great. Now let's look at using this equation to make some predictions. If we're going to predict the hand span, the y value, for a child who has a height of 114 centimeters, we're going to put in x as 114 and use the equation. When we put that value in for x, we can use the equation to find out we predict the hand span for this child to be about 15.38 centimeters. Since 114 is smaller than any of the values we were originally given for x, this is an example of extrapolating. Our other example is to predict the height when we know the hand span, keeping in mind that height is x and hand span is y. So now our prediction will look like this. Now we fill in the y value and use our solving skills to figure out x. We predict that based on a hand span of 24 centimeters, the height is going to be just a little larger than 187 centimeters. And again, since this hand span of 24 centimeters is larger than any of the y values we were given, this is another example of extrapolating. If you need to, rewatch any portions of this video to make sure that you get all the notes and understanding you need. When you're ready, move on to the second regression video, which will cover quadratic and cubic regressions.